Hi everyone, good afternoon. I'm pleased to introduce Sepehr Hajebi, who is currently a postdoc here and actually graduated Waterloo with a PhD and won the Graduate Research Excellence Award and the Mathematics Doctoral Prize, and is also a finalist for the Governor General's Gold Medal for his work on subgraphs and tree decompositions, and will soon join Princeton as faculty. So we still have him in the meantime, and so he'll tell us about minors today. Thank you.
All right. Okay, thank you. Thank you everyone for coming, and thanks for the invitation. So I'll be talking about some joint work with Sophie Spurkel and Maria Chudnovsky. And mostly I'm going to be showing you the statement of a theorem that we proved and tell you about a couple of its applications. But I also do have some slides at the end about some proofs, but that's optional. So please feel free to interrupt and ask questions. I like it when talks are interactive. All right, so I'm going to start up with a question. So you see, I like structural graph theory, which means almost always I'm thinking about either graph minors or induced subgraphs. And graph minor theory is very much about if you exclude a large graph, a large complete graph, as a minor, then the graph you're dealing with is not complex anymore. You more or less know the structure of the graph, and you can use it in all sorts of ways. And induced subgraph theory is very much about if the graph you're dealing with is complex, then what induced subgraphs you should be expecting to be present in your graph. And if you put these two together, then this question comes up. That if I have a graph that contains a large complete graph as a minor, then what induced subgraphs are unavoidable. So let me also recall some of the definitions here. So again, I think as everyone knows, there are three basic operations that you can perform on a graph to make it smaller. You can remove vertices, you can remove edges, you can contract edges. And different combinations of these three operations give you different containment relations on graphs. So you have subgraphs, which you get by removing vertices and removing edges. And you also have minors, which you obtain by removing vertices, removing edges, and contracting edges. And each one of these containments has an induced version. And the induced version is the same, except it disallows removing edges. So induced containment is very much about whenever you're keeping two vertices that are adjacent, you must keep the edge between them. So induced subgraph means you only remove vertices, and induced minor means you only remove vertices and contract edges. Right, and this question over here happens to be a very important one. And in order to convince you why, I need to tell you about treewidth. So what is treewidth? Treewidth is this graph parameter. And I mean, I know of at least 5 different ways to define it. You can define treewidth using tree decompositions, using click sums, using chordal completions, using cops and robbers if you're interested in games. And you can also do this one over here, which is my favorite, but I've also seen it less often. And this has to do with this well-known fact known as the Hajebi property of subtrees. And what does that say? That says that if you pick a tree and a bunch of subtrees of your tree, such that each pair of subtrees intersect in at least one vertex, then they all must intersect in at least one vertex. So if you have a bunch of subtrees of a tree that are pairwise intersecting, then some vertex of your underlying tree belongs to all of them. But what if only some pairs of subtrees are intersecting and some are not? So if you think about it for a moment, I have this set of objects, the subtrees, and I'm declaring some pairs of them to be in a relation, in this case, being intersecting in at least one vertex. So what is that? What is a set of objects and some pairs of them are in relation and some pairs are not? That's a graph. And the treewidth of that graph is the best you can do. So here's the definition. The treewidth of a graph G is the smallest non-negative integer k for which you can find a tree and a subtree of your tree corresponding to each vertex of your graph G, such that whenever two vertices in your graph are adjacent, the corresponding subtrees intersect. And at the same time, each vertex of the underlying tree falls into at most k of your subtrees. I mean, actually you have to say k plus 1 over here because Robertson and Seymour wanted trees to be graphs of treewidth exactly 1 and not 2, but that's the only reason. Right, so that's the definition of treewidth. And if you take this whole slide and replace each appearance of the word tree with the word path, you get the definition of what is called the path width of a graph. Oops. Okay. Right, so we have tree width and path width, and for instance, the Hajebi property of subtrees or subpaths tell you that complete graphs have arbitrarily large tree width and path width. So if you have t plus 1 vertices, then the path width and the tree width are equal to t. Okay, now, okay, there are all sorts of nice things about treewidth, and one of its most convenient features is that it is monotone under taking minors. So if you have graphs G and H, and G contains H as a minor, then the treewidth of G is at least as big as the treewidth of H. And the converse to this is not true, not even qualitatively, meaning not even if the treewidth of G is much, much bigger than the treewidth of H, as long as your graph H is not planar. Why? Because there are planar graphs of arbitrarily large treewidth. So for every positive integer t, if you think about the t by t hexagonal grid, and you're seeing a picture here when t is equal to 4, it is also known as the t by t wall. This is a planar graph of treewidth exactly t. So if your graph H is not planar, there are graphs of larger and larger treewidth that never contain your graph H as a minor, because planarity is preserved by taking minors. And then Robertson and Seymour proved in mid-80s this amazing theorem that the converse is true if H is planar. So fix a graph H, then graphs of sufficiently large treewidth contain H as a minor if and only if H is planar. So this is called the grid theorem, and another way to think about the grid theorem is every graph of sufficiently large treewidth is going to contain your favorite wall as a minor, or equivalently some subdivision of your favorite wall as a subgraph. And there's a similar story for path width. Again, if you have a graph G that contains a graph H as a minor, then the path width of G is at least as big as the path width of H, and the converse is not true. And remember, trees are graphs with treewidth 1, but there happen to be trees of arbitrarily large path width. So if you think about a binary tree, a full binary tree, then the path width is half the radius or height, whichever you call it, rounded up. So as long as your graph H contains a cycle, is not a forest, the converse is not true because there are trees of arbitrarily large path width, and taking minors keep you in the class of all forests. And again, Robertson and Seymour proved that the converse is true if H is a forest, meaning it doesn't contain a cycle. So for every forest H, every graph of sufficiently large path width contains H as a minor. And again, equivalently, you can say that every graph of sufficiently large path width contains your favorite binary tree as a minor, or some subdivision of your favorite binary tree as a subgraph. So we know what are the unavoidable minors and subgraphs of graphs with large path width. And we know what are the unavoidable minors and subgraphs of graphs with large tree width. And this should be more than enough motivation to ask, what about induced subgraphs? So if I give you a graph and I tell you that the tree width is huge, then what induced subgraphs are going to be present in the graph? And so this is the central problem that I, with my co-authors, have been thinking about for the past 5 years or so. And it is still open, and I'm not going to get into much details, but let me give you at least one explanation why this should be a drastically more complicated situation compared to the case of minors and subgraphs. So you see, if the grid theorem is easily seen to imply the following, that if you pick a graph class H that is closed under taking minors, then this class of graphs is a valid set of minor obstructions to bounded treewidth, meaning every graph of sufficiently large treewidth contains some graph in here of large treewidth as a minor, if and only if this class contains all planar graphs. So a minor closed class of graphs is a valid set of obstructions to bounded treewidth for minors, if and only if it contains all planar graphs. And actually, this also implies the grid theorem, but if you think about the same thing for induced subgraphs, then your class H must contain all graphs. So if you have a graph class H that is closed under taking induced subgraphs, and every graph of sufficiently large treewidth contains an induced subgraph of large treewidth that comes from your class, then this class contains all graphs. So what does this mean? It means that if there's ever going to be a list of constructions of induced subgraph assertions to bounded treewidth, if the answer to this question is ever found, then if you just put them all together and take the closure under induced subgraphs, then you see all graphs. So whatever the answer to this is going to be very complicated. And by the way, this doesn't mean that you shouldn't be thinking about this problem. I mean, this is a quote from their paper that this puts an end to this endeavor. It really doesn't. I mean, for instance, think about Hamiltonicity. I mean, here's your favorite graph. G on, I don't know, 5 vertices. And I'm going to add 6 more vertices. And I'm going to add these edges. So this is another graph. And this is Hamiltonian. Here's a Hamiltonian cycle. And it contains your favorite graph G as an induced subgraph. I'm just going to remove these vertices. And I get exactly my graph G that I started with. So what does it mean? It means if you just put all Hamiltonian graphs together and take the closure under induced subgraphs, you see all graphs. It doesn't mean you shouldn't be thinking about Hamiltonicity. If anything, it means you should be thinking about Hamiltonicity. Right. Anyway, so the induced subgraph problem is hard. The minor problem is easy, or has been done. So let's think about something in between. What is between minors and induced subgraphs? Induced minors. So what are the unavoidable induced minors of graphs with large treewidth? And again, remember, induced minor means I'm only going to remove vertices and contract edges. I don't remove edges. Right, so we need to have planar graphs again, because walls have arbitrarily large treewidth. But we also need to have complete graphs, because complete graphs have arbitrarily large treewidth. And because I'm not removing edges, whatever induced minor of a complete graph I take, it's going to be a complete graph again. So this is the difference between the case of induced minors and the case of minors. And this happens to be sufficient as well. So it's long been known that every graph of sufficiently large treewidth contains either your favorite planar graph or your favorite complete graph as an induced minor. And for the complete graph, I'm writing minor here, not induced minor, because for complete graphs, minors and induced minors are the same, because I'm not removing edges. So, right. I mean, this may have 2 potential advantages. First of all, is it more approachable? Yes. I mean, this has been known for a long time, and the proof is actually not that difficult compared to all the machinery that's been developed. But could this be used as a stepping stone to solve the induced subgraph problem? I mean, we're at induced subgraphs, and we know the answer for minors. We backed it up for a moment to induced minors, and we want to see if there is any way to use this so we can get closer to a solution to the induced subgraph problem. So let's see. I mean, I have the outcomes over here, a large planar graph as an induced minor and a large complete graph as a minor, and I want to see if I can turn them into induced subgraphs. So yeah, this is what I just said. And for the planar induced minor, we are good, because it is well known, and it's easy kind of to check, that if you contain a sufficiently large wall as an induced minor, then it implies that your graph contains either some subdivision of your favorite wall or the line graph of some subdivision of your favorite wall as an induced subgraph. And in the unlikely event that you don't know what a line graph is, don't panic. It simply means, at least here, that you're essentially going to turn each one of these claw junctions into a triangle junction. And what you get is a graph of pretty much the same treewidth. So the planar induced minor outcome is good. So what is the second outcome? It'd be a complete minor. And what do I want? I want to see if it's going to give me some nice induced subgraphs. And we're back at the question that we started the talk with. If I give you a graph with a huge complete minor, then what induced subgraphs are unavoidable? So this is why that question is important. If there's ever going to be an answer to that question, it immediately solves the problem of what are the unavoidable induced subgraphs of graphs with large treewidth. And again, this doesn't seem to be as useful as a tool to solve the induced subgraph problem, because complete minors are just way too complex to extract any interesting induced subgraph from. So how can we fix this? How can we turn this into something that may actually be useful? So, okay, remember we need to have a planar induced minor as an outcome. That's unavoidable. But because we're not removing edges, we also need to have some really dense non-planar outcomes. And one easy candidate is a complete graph. And if I just put the complete graph in, it's going to be this. And this turned out to be too easy to prove and too difficult to turn into anything about induced subgraphs. So what is another candidate for a dense non-planar graph that I could put in here? Complete bipartite graphs. Complete bipartite graphs also have large treewidth. If you think about the complete bipartite graph KTT, for instance, you can just contract a perfect matching, and what you get is a large complete graph as a minor. So you contain a large complete graph as a minor, it means the treewidth is large. And containing a large complete bipartite graph as an induced minor is different than containing it as a minor. So this is the difference between complete bipartite graphs and complete graphs. Why? Because in complete bipartite graphs, you have pairs of non-adjacent vertices. So I'm just going to charge ahead and replace the complete minor outcome with a complete bipartite induced minor outcome in the previous theorem and say, okay, is this true that every graph of sufficiently large treewidth contains either a large planar graph or a large complete bipartite graph as an induced minor? As an induced minor. So this is false. Why? Because of complete graphs. I mean, complete graphs of arbitrarily large treewidth. And again, because I'm not removing edges, I need to have complete graphs in one form or another among the outcomes. But if I put them back in as minors or induced minors, it's going to be the same as here. So I'm going to put them back in, but as subgraphs or induced subgraph, which is the same again because I'm not removing edges. So here's the question. Is it true that every graph of sufficiently large treewidth contains either a large planar graph as a minor or a large complete bipartite induced minor? Sorry, the planar graph also should be as an induced minor, or a large complete subgraph. At least complete subgraphs, I mean, complete graphs are not a counterexample to this anymore. So could this be converted into a theorem about induced subgraphs? Again, the complete subgraph is just what it is. We don't need to do anything with it. And the planar induced minor we can handle. It gives us either a subdivision of a large wall or the line graph of a subdivision of a large wall as an induced subgraph. And the complete bipartite induced minor is what I'm going to tell you about today. So I'm going to show you the statement of a theorem, at least, and maybe some words about the proof, that tells you exactly what are the unavoidable induced subgraphs of graphs with a huge complete bipartite induced minor, and also excluding some fixed planar graph as an induced minor. So excellent, we got it. We have all the outcomes to be induced subgraphs, and we're done. Except there's still a small problem. Who said this conjecture is true? And in fact, it is not. But you're seeing a green cross here, which means this conjecture is false. There's a counterexample, but it doesn't mean what we're doing is useless. So let me show you a couple of applications. For instance, you don't need to ask this question for every planar graph. I mean, for some planar graphs, it is false. And for some others, it may be true. In particular, it turns out to be true if the planar graph you're excluding is a forest. And in that case, actually much more is true, that you only need to assume that the path width is large. So we prove that every graph of sufficiently large path width contains either your favorite forest as an induced minor, or a large complete bipartite induced minor, or a large complete subgraph. And this can be turned into a theorem with induced subgraph outcomes. Why? Because the complete subgraph is what it is. The complete bipartite induced minor is the theorem from this talk. And for the case of forests, you can do the same thing as the case of general planar graphs, because it is easy to see that a sufficiently large binary tree contained in your graph as an induced minor implies that you either get some subdivision of your favorite binary tree or the line graph of some subdivision of your favorite binary tree as an induced subgraph. So what just happened? I started with a graph of large path width, and I got all the outcomes to be induced subgraphs. So this means now I have a full characterization of what are the unavoidable induced subgraphs of graphs with large path width. So you remember this overarching question we had, that what are the unavoidable induced subgraphs of graphs with large tree width? Now we have the answer to the analogous question for path width, which we're really happy about. Right. So this is one application. The other application that I'm just going to mention in passing, because I'm really fond of it, has to do with this conjecture of El-Zahar and Erdős about chromatic number. So one piece of terminology. If you have a graph G, two induced subgraphs of your graph are said to be anti-complete if they're disjoint and there are no edges between them. And El-Zahar and Erdős conjectured that every graph of sufficiently large chromatic number contains two anti-complete induced subgraphs of large chromatic number. So two induced subgraphs of large chromatic number with no edges between them, disjoint and with no edges between them. Except this would be false because complete graphs have arbitrarily large chromatic number, and you can't find two anti-complete induced subgraphs that are both non-empty. So you have to make room for a large complete subgraph as another outcome. And the conjecture is that would be enough. And then we thought about it a little bit, and we proved something very similar about treewidth, that every graph of sufficiently large treewidth contains two induced subgraphs that are anti-complete, and they have relatively large treewidth, or the graph contains a large complete induced minor, complete bipartite induced minor, or a large complete graph as a subgraph. And again, you can use the theorem from this talk and turn the complete bipartite induced minor into induced subgraph outcomes, and this gives you a full analog of the El-Zahar and Erdős conjecture for treewidth with only induced subgraph outcomes. Actually, it turns out that complete graphs, complete bipartite graphs, and one more construction is all you need to deal with when you're thinking about induced subgraphs. So every graph of sufficiently large treewidth has either two anti-complete induced subgraphs of large treewidth, or a large complete subgraph, or a large complete bipartite induced subgraph, or another counterexample that we have to be careful about. Okay, so these are the two applications. And right, now I'm going to start telling you about the main theorem. And what's going to happen is that from now on, I'm going to say the word constellation about 50,000 times. So let me tell you what it actually means. So what are some examples of graphs with a huge complete bipartite induced minor? For instance, complete bipartite graphs themselves. You don't need to contract edges, you don't need to remove vertices, you don't need to do anything. And a constellation is essentially just a complete bipartite graph. And on one side of the bipartition, I'm going to keep the vertices in the stable set. And on the other side, I'm going to stretch them out into paths. So a constellation, an SL constellation, is a graph that consists of a big stable set of vertices and a set of pairwise disjoint and anti-complete paths, so there are no edges between the paths. And every vertex in the stable set has at least one neighbor in each path. And if you think about it for a moment, if your graph contains a large constellation as an induced subgraph, what you can do is you can remove the vertices that are not in the constellation, and then you just contract these edges along the paths. In other words, you just contract the path into one vertex. And that's going to give you a big complete graph, complete bipartite graph. So what did I just do? I started with my graph G, and I only removed vertices or contracted edges, and I got to a big complete bipartite graph. So the graph contains a big complete bipartite induced minor. So if your graph contains a large constellation, then it contains a large complete bipartite induced minor. And the first part, the first half of our main result is that the converse is also true. That any graph with a sufficiently large complete bipartite induced minor, which also excludes some fixed planar graph as an induced minor, is going to contain a constellation as an induced subgraph that is as big as you want. So essentially, you just need to think about induced minors, complete bipartite induced minors that look like this. On one side, I just have vertices, and the other side, I just have paths. And okay, this is nice. This is something about what induced subgraphs you would expect to see. And this is quite elucidated compared to a random complete bipartite induced minor in your graph. But still, I mean, the adjacency between the stable set and the paths of the constellation could be quite wild. So it would be nice if we could just say something about those edges as well. And that is the second half of the main result that I'm going to spend pretty much the whole rest of the talk and tell you about. So essentially, it turns out that you only need to think about two types of constellations. The first one is what we call interrupted constellations. So what does it mean for a constellation to be interrupted? It means, first of all, the vertices in the stable set are not going to have common neighbors on the paths. And the second condition is that you can linearly order the vertices in the stable set so that for every choice of 3 vertices, the third one is going to have at least one neighbor in every path that goes from the first to the second. In other words, if I just remove the neighbors of the third one from the graph, the other 2 vertices are going to be separated. There's not going to be any path left between them. So here is a picture of an interrupted 4-1 constellation. There are 4 vertices in the stable set and just one path. And let me just tell you where is it coming from. So I have this stable set of 4 vertices linearly ordered and this path. And what are the rules? Every vertex in the stable set is going to have at least one neighbor in the path. That's what it means to be a constellation. And every vertex in the path is going to have at most one neighbor in the stable set, meaning vertices in the stable set do not have common neighbors in the path. And now, the first and the second vertex can do whatever they want. From the third vertex on, I need to be careful about the paths between x1 and x2. So I'm going to think about the gaps along L between consecutive neighbors of x1 and x2. And I insist, I don't need to care about the paths or the gaps between consecutive neighbors of the same vertex. And x3 is supposed to have at least one neighbor in each one of these gaps. And that's the only requirement. It can do whatever else it wants. So here we go. And then I'm going to think about the gaps between the neighbors of x1, x2, x3. And x4 is going to have at least one neighbor in each one of them and can do whatever else it wants. So you get the idea. So that is the first example. The second example is what we call a disrupted constellation. Even though the name doesn't suggest, it is the exact opposite of what an interrupted constellation is. So in a disrupted constellation, again, you need the vertices in the stable set to not have common neighbors in the paths. And for every choice of 3 vertices in the stable set, the middle one is going to have at least one neighbor in every path that goes from the left one to the right one. So whenever I choose 3 vertices, xi, xj, xk, then xj is going to have at least one neighbor in every path p that goes from xi to xk. In other words, vertices in between with no neighbors in this path do not exist. And I also need to parameterize this. So I'm going to introduce this parameter q. Okay. And I'm going to say a constellation is q disrupted if, again, the vertices in the stable set do not have common neighbors in paths. And for every choice of q plus 2 vertices, one on left, one on right, and q vertices in between, every path that goes from this one to that one contains at least one neighbor of one of these q vertices. So if I put q is equal to 1, that's going to be what used to be called disrupted. In other words, for every path between xi and xk, there are fewer than q vertices in between that do not have any neighbors in that path. Okay, so a quick recap. Interrupted means for every choice of 3 vertices, the last one is going to have at least one neighbor in every path between the other 2. Disrupted means for every choice of 3 vertices, the middle one is going to have at least one neighbor in every path between the other 2. So before we move on, let me also show you a couple of examples of disrupted constellations. Here is the easiest one. This is what we call an alignment. So what is an alignment? It's a constellation in which you can linearly order the vertices such that for each path, when I traverse the path from one end to another, I see the neighbors of the vertices in the stable set in the exact same order. So I first see the neighbors of x1, and then the neighbors of x2, and the neighbors of x3, and so on and so forth. And clearly, these are disrupted, or one disrupted. Because whenever you have a path from x1 to x3, clearly x2 is going to have at least one neighbor in it. So the other example, which is a counterexample to something, maybe I should mention that it would really be nice if these were exactly the only disrupted constellations, right? I mean, being disrupted means I'm just going to have all the neighbors of x1, x2, x3, so on and so forth, just lined up along the paths. And what I'm going to tell you next is that is not true. And there's going to be a counterexample to this. So we have disrupted constellations that do not look like that. And in order to do that, I need to tell you about strings of numbers. So I'm going to define this sequence of the strings of numbers, which I'm going to call the zigzag strings. So, and the definition is recursive. So for every positive integer n, the string zn has numbers 1 up to n as its element or character, if you would. And z1 and z2 are just 1 and 1 and 2. And from the third term on, what I'm going to do is I'm going to start with, so if I want to construct zn, I'm going to start with 1, and then I'm going to go up like zn minus 1. I'm going to come back down like the inverse of zn minus 2, and then I'm going to go up like zn minus 1 once again. And if you write this down, you're going to get z3, z4, z5, z6, like this. So I mean, this I don't think is quite illustrative, so let me show you a picture. Okay, so here are z1 and z2. z1 is just 1, z2 is 1 and 2. And if I want to construct z3, I'm going to start with 1, and then go up like z2, and then I'm going to come back down like the inverse of z1, but z1 doesn't move at all, so I'm not going to do anything. And then I'm going to go up like z2 once again. For z4, I'm going to start with 1, I'm going to go up like z3, and I'm going to come back down like the inverse of z2. So z2 goes up, I'm going to come back down. And then I'm going to go up like z3 once again. Let's see another example. For z5, you start with 1, you go up like z4, you come back down like the inverse of z3. z3 goes up, up. So I'm going to come back down, down. And then I'm going to go up like z4 once again. And I'm just going to stay silent and show you a picture of z6. Okay. So, and then I'm going to use these strings and construct a constellation. So a zigzag constellation is a constellation in which, again, as usual, the vertices in the stable set do not have common neighbors in the paths. And you can traverse each path from one end to another so that the neighbors of the vertices in the stable set, according to some linear order, appear along the path exactly like the sequence z, whatever is the number of vertices in the stable set, zs. So for instance, if you remember what used to be z6 over here, I'm just going to rotate this by 90 degrees, and it's going to be the picture over here that you can see. And this is just going to be one of the paths of the constellation. You may have many of them. And this constellation over here is also disrupted. You can convince yourself it's not that difficult to see that if there's going to be a path between x2 and x5, then x3 and x4 must have neighbors in it. And yet it doesn't contain not even an alignment with 4 vertices in this stable set and just one path. It never contains an induced subgraph that looks like this. So there are disrupted constellations that are just not alignments, not in any possible way. Okay, so we have interrupted constellations, which are fairly easy to figure how do they look like, and disrupted constellations, which are pretty difficult to figure how do they look like. There might be pretty wild examples like this. And it turns out that's enough. So these are the only 2 types of constellations you need to think about. If your graph sheet contains a huge constellation, then either it contains, and this time you don't need to think about planar graphs. You can actually think about any graph you want. Every graph that contains a huge constellation contains either your favorite graph H as an induced minor, or it contains a large interrupted constellation, or it contains a large disrupted constellation. And disrupted here is parameterized, and the parameter is the number of vertices of the graph H you started with. So you need to think about the size of the constellation here, S prime and L prime, to be just gigantically larger than the number of vertices of H or any function of that. So you get to have a huge, huge constellation that is just a little disrupted. Okay. So does anybody think there is anything wrong with this theorem? I mean, where are complete bipartite graphs? I mean, when we're defining these, we insisted multiple times that the vertices in the stable set do not have common neighbors in the paths. It means there's never going to be a complete bipartite graph just sitting in the graph as a subgraph or induced subgraph. But complete bipartite graphs are constellations. And this is a theorem that tells you what you would expect to see in any graph that contains a sufficiently large constellation. So all of this is just to tell you that you need to have complete bipartite graphs as another outcome. So every graph with a sufficiently large constellation contains either your favorite graph as an induced minor, or a large interrupted constellation, or a large disrupted constellation, or just a large complete bipartite graph as an induced subgraph. And all outcomes here are just induced subgraphs, so this is pretty much as good as it gets. Okay, I think I have about 20-something more minutes. And I'm going to tell you a little bit about the proof of this. Okay, does anybody have any question about the statement? Good. Okay, and before we move on, let me just tell you about some beautiful analogy that I actually I'm pretty fond of. And I mean, this doesn't tell you anything about the math here. It's just something that I really enjoy talking about. I mean, so what are some examples of connected graphs? I mean, a path is a connected graph, and a big star is a connected graph. And this is a pretty well-known fact. I mean, you would see this in the first course in graph theory. I mean, I hope. That if you have a sufficiently large connected graph, then it does contain either a big star or a long induced path. So stars and paths are unavoidable induced subgraphs of sufficiently large connected graphs. I mean, stars are subgraphs because you may contain a big clique, but. And if you think about it for a moment, here, I can think about some sort of a graph that is associated with a constellation. So if you have a big constellation, just think about the stable set, and for every pair of vertices, ask, can these two make it to each other with a path that is not interrupted by neighbors of anybody else in the stable set? And if so, just put an edge between them. This is this visibility graph that you can associate with your constellation. And if you think about it for a moment, interrupted constellations are exactly those constellations in which this visibility graph is just a big star. Because the top vertex of the constellation, in the linear order, that vertex sees everybody else. But the other vertices are pairwise just not seeing each other because this guy is interrupting all of them. And if you think about a disrupted constellation, it means that you can linearly order the vertices such that every vertex is only seeing the two vertices that are immediately to the right and to the left. Because if they want to jump over the vertices in between, they're going to have neighbors in it. And one other fact that you could easily figure is that this visibility graph, for whatever constellation you started with, is always connected. Because you have neighbors in a big path, and eventually you're going to be able to get everybody and make it to everybody. So a big constellation gives you either a big interrupted constellation or a big disrupted constellation. A big connected graph gives you either a big star or a big path. I mean, I like this analogy, but unfortunately it really doesn't help with proving this. So what actually does help with proving this is this pretty useful theorem that we call, the hypergraph lemma. So let me tell you a little bit about the hypergraph terminology I'm going to use. Again, so I think we all know what is a hypergraph. It's a set of vertices, a set of edges, and there's an incidence relation. You can think about it as a 0-1 matrix. So what is a matching in a hypergraph? It's a set of edges or hyperedges that every vertex is incident with at most one of them. What is a vertex cover in a hypergraph? Is a set of vertices such that every edge or hyperedge is incident with at least one of them. And again, I think it's pretty easy to see that no matter how small of a vertex cover you choose for your hypergraph, it is always going to be at least as big as the size of the biggest matching in your hypergraph. And I mean, we know a lot of different cases in which these two are actually the same, right? I mean, Koenig's theorem tells you that in bipartite graphs, these two are the same. And in general, in any graph, sure, I mean, the minimum size of a vertex cover is not necessarily the same as the maximum size of a matching, but it is at most twice the maximum size of the matching. I mean, if you just pick a maximum matching, then the whole vertex set of the matching is a vertex cover. But for hypergraphs in general, this is not true. And here's a counterexample. You start with a big complete graph, and you can think about a complete graph as a hypergraph, I mean, because graphs are hypergraphs. So just think about it as a 0-1 matrix, and think about the transpose of the matrix. I mean, this is not really what happens when you transpose, but anyway. In other words, you think about it as a hypergraph, and you swap the role of vertices and edges. So in my hypergraph, the vertices are going to be the edges of the complete graph. And the hyperedges are going to be the stars centered at the vertices. This is, I think, what you would call the dual hypergraph of a big complete graph. And if you think about it for a moment, it's not difficult to see that, first of all, this hypergraph over here doesn't have a matching of size 2. I mean, if you pick any two hyperedges, because they correspond to two vertices in the graph, there is an edge between them, and that edge is a vertex of the hypergraph that belongs to both hyperedges. And at the same time, if you want to hit all hyperedges, you're going to need at least half the number of vertices rounded up, vertices in your vertex cover. So there are hypergraphs with no big matching and also no small vertex cover. And there's this lovely theorem of Ding, Seymour, and Winkler from the year I was born, actually, that this is the only counterexample. So just think about, let's define lambda of your hypergraph to be the maximum L for which something like this sits in your graph. So you can find L hype in your hypergraph. You can find L hyperedges such that for every two of them, there is some vertex of the hypergraph that belongs to those two hyperedges, is incident with those two hyperedges, and with no other hyperedge among these L hyperedges. So L hyperedges such that for every two of them, there is some vertex that is incident with those two and with nobody else. And they prove that if your hypergraph has no big matching and also this parameter lambda is bounded, then it does have a small vertex cover. So in some sense, this dual hypergraph of a big complete graph is the only counterexample to no big matching implies small vertex cover. Okay, so how do we use this? I mean, you don't need to read all of this. I'm going to explain it. But so I think the first step is, if you remember when we were defining interrupted and disrupted constellations, we insisted that the vertices in this table set do not have common neighbors in the path. But a big enough constellation that I start with, it doesn't necessarily have this property. So let's just convince it to have this property. And remember that I'm excluding some fixed graph H as an induced minor. So for each path of the constellation, path L, I'm going to define a hypergraph that I'm going to call gamma L. So the vertices of the hypergraph are the vertices of the path. And the hyperedges of the hypergraph are the vertices in the stable set. And the incidence is who is adjacent to who in this graph view. So, okay, can this hypergraph contain a big matching? If it contains a big matching, it means there are a lot of vertices here such that they do not have common neighbors along these paths. And okay, before I move on, because I can assume that the number of paths is much, much bigger than the number of vertices in here, I can actually assume that this hypergraph is the same for all of these paths, because there are only so many hypergraphs with this being the set of hyperedges, if the number of paths is big enough. So if this hypergraph has a big matching, then it means there's this big set of vertices in here such that no two vertices in here have a common neighbor on this path. And because the hypergraph is the same for all of the paths, it's going to be the same for all of them, and that's what I wanted, right? I wanted a big sub-constellation in which vertices in this table set do not have common neighbors in the paths. So big matching is not going to be there, or I'm done. What if, I think that should be lambda. There is a typo here. What if that parameter lambda is big? It means there are very many hyperedges in here, such that for every two of them, there is some vertex that is incident with those two and with nobody else. So what does that mean? That means you have this big complete graph that is exactly once subdivided. So every edge is subdivided exactly once. And your graph contains this as an induced subgraph. And remember, we started with the assumption that some fixed graph H is excluded as an induced minor. And now that I have this big one subdivision of a complete graph as an induced subgraph, what I'm going to do is, whenever in this graph H is an edge between two vertices, I'm going to keep this 2-edge path. I'm just going to contract this edge. Then it turns into an edge. And whenever there is a pair of non-adjacent vertices, I'm just going to remove this one vertex over here. So what happened? I started with my graph, and I got to my graph H. I started with the big constellation G, and I got to my graph H by only removing vertices or contracting edges. So that's not going to happen because I'm excluding this as an induced minor. So the parameter lambda is not going to be large, which means by the hypergraph lemma, you're going to have a small vertex covering this hypergraph, meaning there's going to be a small set of vertices here such that every vertex in the stable set is adjacent with at least one of them. So if the number of vertices in the stable set is huge enough, then some vertex in the path is going to be adjacent to many vertices in the stable set. And this is going to happen for all of the paths because the hypergraph is always the same. Now what is this? A big stable set over here, a big stable set over there, and every vertex here is adjacent to every vertex in there. That's a big complete bipartite induced subgraph. That's one of the outcomes. Okay, so because I'm assuming that a big complete bipartite induced subgraph is not going to be there, or I'm done, I can actually assume that the vertices in the stable set of the constellation do not have common neighbors. That's the first step. So the second step is, okay, now here's my constellation. And remember, there is this fixed graph H I'm excluding as an induced minor. Let's assume that it has exactly little h vertices. So for every fixed size subset of the set of vertices, the stable set of vertices of the constellation, the one with size h, I'm going to ask, is it true that for every two vertices in here, there is a path between them that nobody else in this set has neighbors in it? And if the answer turns out to be yes for all pairs, it's the same thing. It's a big subdivision of a complete graph sitting in my graph as an induced subgraph. This means I can get to my graph H as an induced minor, same as in here. I mean, the only difference is that it might be a bigger subdivision, but it doesn't matter. I'm either contracting edges or removing vertices. So for this set A, the answer is going to be no for some pair of positions between 1 up to h. So there's this two positions I and j, which I'm going to associate with this set A, and they're both coming from the set of numbers from 1 up to h, such that every path between the ith vertex and the jth vertex contains a neighbor of somebody else in this set A. So, and I'm going to color that set A with that pair of numbers, and there are only, I don't know, 8 choose to different colors that I'm using. And now I can use Ramsey's theorem. If this set of vertices is big enough, I can go to a big subset such that for every subset of that big subset of size h, the color is always the same, meaning the disruption is happening between the same pair of vertices. The pair I and j is always going to be the same. This is just an application of the standard version of Ramsey's theorem. Good? Okay, and that was the second step. And the third and last one is to actually use all of this. So here is my big constellation, and I can assume that I have this property over here, that for every fixed size subset, there are these two positions such that every path between these two is interrupted by neighbors of somebody else from this set. But only if these two vertices were actually the first and the last are we done, because that is what the definition of a disrupted constellation was, right? For every set of H vertices, every path between the first and the last contains a neighbor of somebody in between. So the problem is that this I and J might actually be somewhere in between. And I mean, because I can just flip everything this way, I can assume that, for instance, I is not just 1. It is, I don't know, something bigger than 2. So what I'm going to do now is to try to push I to the left. So there's this linear order of vertices here. And think about the first vertex. Let's call it x1. And now think about the neighbors of x1 along one path. And this is going to give you the gaps within consecutive neighbors. So I'm going to define a hypergraph associated with this path. And the vertices of the hypergraph are going to be these gaps. The edges of the hypergraph are going to be the vertices over here, except for x1. And the instance is going to be, does this vertex have a neighbor in this gap or not? So think about this hypergraph. Again, by pigeonhole, I can assume that this hypergraph is always the same for all of the paths, for most of the paths. So can this hypergraph contain a big matching? What does it mean to contain a big matching? It means there are a lot of these vertices over here, which are the hyperedges of the hypergraph, such that for every gap, at most one of them is going to have neighbors in it. What does that mean? That means if you pick any two vertices in here, if they're going to make it to each other using a path, they must go through a neighbor of this guy, because they're not going to have neighbors in the same gap. And what does that mean? That means that this vertex is really like the top vertex of your interrupted constellation. It is the vertex that is interrupting all the paths between all pairs of vertices that are coming below. So you just think about this as the top vertex, and you repeat this sufficiently many times. Eventually, you get your interrupted constellation with the desired number of vertices in the stables. So a big matching is not going to happen, or I'm done. And what if the parameter lambda is big? It means, again, for a lot of pairs of vertices in here, for each pair, there is one gap that these two have neighbors in it, and nobody else has neighbors in it, which means they can make it to each other with a path that is not going to contain neighbors of anybody else, and the same thing is going to happen. You contain a proper subdivision of a B-complete graph as an induced subgraph, and that gives you your graph H as an induced minor. So by the hypergraph lemma, this hypergraph is going to contain a small vertex cover, which means there are going to be only a few of these gaps such that every vertex here, except for x1, has neighbors in at least one of them. And because there are very many vertices in here, there's one gap that most of them are going to have neighbors in it. And what does that mean? That means just think about those vertices in here. They all have neighbors in this gap. If I pick any subset of size h minus 1 of those, I'm going to put x1 to the left of this, and that will be a subset of size h. And by the property I have from the previous step, the one over here, I know that the interruption is happening in the I and j position, between the I and j position. But actually, I can forget about x1 because x1 doesn't have neighbors inside this gap. So the interruption is not happening because x1 is there. So the interruption is happening by one other vertex in here, which means now I is actually I minus 1. It's been pushed to the left by 1. So you do this sufficiently many times, and eventually I is going to be 1, and j is going to be whatever is the last number, and you're done. You're getting your disrupted constellation. OK, I think that's about it. I'm going to stop here. Thank you.
Thank you. Are there any questions?
What projector was that?
Oh, this one. This one. That for every planar graph, if you have sufficiently large tree width, then you contain either that planar graph or a B-complete bipartite induced minor or a large complete subgraph.
I'll also jump in then. So this is a bit of a long shot, but I've seen tree width appear sometimes in computer science and kind of complexity theory results that you say, you know, the complexity of some problem is the tree width of some sort of graph that the problem is related to. Have you seen any applications of these, you know, kind of induced minor theorems being applied to these sorts of other?
Yeah, I mean, so for instance, there's this whole line of work on, so we've always been talking about what should I exclude so that the treewidth of the graph is absolutely bounded. And you don't need to always think about that if you're just concerned with algorithms. If you get the treewidth to be logarithmic in the number of vertices of your graph, it turns out that whatever application, pretty much all the applications of bounded treewidth are actually going to be in your favor when you have treewidth logarithmic in the number of vertices. And there are a whole lot of theorems about if you exclude this and that and that and that as an induced minor, as an induced subgraph, then the treewidth may not be bounded. And there are counterexamples telling you that the treewidth is not bounded. But it happens to be logarithmic, which means at least as long as the algorithmic applications are concerned, this is as good. I mean, I'm not sure if that really answers your question, but that's just one example of.
Other questions? Okay, well, let's thank Sepehr again.